Okay, welcome back, everybody. We are now today moving into chapter 5 of our book, in which we actually encounter for the very first time the derivative. Okay, and much of the machinery that we've been building up for this in this course has been heading towards being able to understand the concepts of calculus. But, of course, with attention to being very rigorous about some of the definitions. So let's define the derivative. This is our plan. We want to understand the derivative and what it means. So last time we talked about, the last few lectures we were talking about continuous functions, and now we're interested in understanding when functions are what are called differentiable. So let's make a definition. We're going to be dealing now with real valued functions. So suppose we have a function that's defined on some interval, ab, a closed interval, and it spits out a real number. We're going to say that this function is differentiable if the following, okay, I have to say where, at x in this interval, ab, I'm going to say it's differentiable at x if this limit exists. Okay, so notice that whatever I'm about to say, that we're going to call this function differentiable if some limit exists. And so the concept of taking the limit of some function is actually very important in this definition. So what function am I going to take the limit of? Well, I'm going to take the limit of a certain function that's a quotient. It's a quotient of f at t minus f at x over t minus x. And if this limit exists, we're going to say this function is differentiable at x. We'll demand that t be somewhere inside. So t is approaching x, but t is not x. Okay, so that's something we're going to demand. And if this limit does exist, we'll give this limit a name. We'll call it f prime at x, because this limit may depend on x. Okay, so here's our definition of what's called the derivative. So this limit is called the derivative of f at x. And it's a function of x. Okay? So that's our first basic definition. Now, I know everybody has seen this definition before, although often in other textbooks, limit is rewritten in a slightly different way. Sometimes you say limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so the picture that you might have in your mind is something like the following. If I take the graph of some function, the function might look like so. And I want to understand, let's say, what's happening at a particular point x. This is the x-axis. And compare that to what's happening nearby. You might call this nearby point x plus h, or you might call it t. And if I compare what's happening, then f of t minus f of h is basically the difference in the height of this function, of this graph of this function. And t minus x is the distance between t, is the length, the interval between t and x, that length. So it's the rise over run. So you can think of it, if you like, as the slope of this secant line. And now what I do in this limit is I say, hey, look at the slope of the secant line as I let t get closer and closer to x. Okay? So this particular expression is a slope of a secant line. And we're now taking the limit of these slopes of these lines. So if that limit exists, well, let's see. In this case, this has a certain slope, and now the next, if I let t get closer, these lines seem to, their slopes seem to converge, at least in this particular picture. And so do you see then that if we have a limit, it's basically going to be, in some sense, the instantaneous limit of this. If you could put a secant line here that was very, very, that subtended the points right at x and a point very close nearby, you'd get the slope of this line, which we often call the tangent line. So this thing has slope f prime at x. Okay, that's the idea. Now, of course, do you see on this side that if you did the same thing with t coming from the left, that you'd get secant lines that look like this, but at least in this picture, those things also converge. Their slopes also converge. Do you see that? Okay. Okay, this is to be contrasted with, for instance, another picture where maybe your function f of x looks something like this. So there's a function. Certainly seems to be, well, it's a function. It's continuous here, in fact, at x. But what's happening if I look at the slope of the secant lines? Well, if you look at any secant on the right-hand side, because this line happens to be straight, you just get that slope, right? Take the limit from the right. Well, that limit from the right actually exists. It converges to this slope. The limit from the left exists for the same reason, and it converges to this slope. But does the limit exist if you consider t on both sides? No. So in fact, this function is not differentiable, which I'll abbreviate diffball, at the point x. Okay? Paul.
Does, for instance, the limit from the left exist at the left endpoint?
At the left endpoint of the interval?
Yeah, of the domain of the function.
Yeah, so if the domain happened to just include everything from x onward, then this thing would be differentiable at the left endpoint. Okay? According to the definition. Okay, you want t to be in the interval, but not the actual point itself. Okay? Yeah, so and of course that should make sense to us, because if I'm only considering this interval, then that limit does exist, right? Because there's nothing, we're not considering anything outside the domain, right? Okay, good. So this corresponds with hopefully what you remember from calculus. So here's some questions that I'll throw out just to see if we're on the same page. So if f is continuous on some interval, is f differentiable necessarily on some interval? Oh, and what does it mean to be differential on an interval? I just mean it's differentiable everywhere inside. Is this necessarily true? No. Can you see an example? Yes, right here. So clearly no. Look at that example. Okay, second question. If f is differentiable on some interval, must f be continuous? On that interval? Some people here are furrowing their brows. If f is continuous, must it be differentiable according to the definition? How many people say yes? Sorry, if f is differentiable, must f be continuous? How many people say yes? Okay, that's actually, it's the right intuition. How do we prove that? Well, it's actually not too hard, knowing properties of limits, right? Limits of, when you're taking a limit of a function, we know that the limit of a product is a product of the limits, yes? And if I want to verify f as continuous, would you agree that it's enough to verify if t converges is converging to x, it's enough to verify that the limit of f of t goes to what? F of x, right? That's what it means for function to be continuous, right? It basically preserves limits. So t goes to x. Is the limit of f of t going to f of x? Another way to say the same thing is the limit of f of t minus f of x going to what? 0. Well, let's just see. Look at this creature. Would you agree that this is the same as, well, the same f of t minus f of x, but you can't stop me from dividing by t minus x and multiplying by t minus x, yes? So this is a limit of a product. So that's the product of the limits. And what's the product of the limits here? What's the limit of this thing, if it exists? F prime. And what's the limit of this thing? 0 if it exists. And if it's differentiable, this exists. And this is clearly 0. So this actually is going to be f prime of x times 0, which is 0. Check. So we've just verified that the limit of f of t is f of x, which is what it means to be continuous. Okay? Okay, good. So differentiable functions are continuous. So they're actually, I'm a little afraid to see what's under here. Ta-da! Actually, it's cool because you could actually make this thing like go up. All right. What fun. Ta-da! Okay. Okay. How? Yes, question.
For continuity, we need the limit of f of t going to f of x, but we also need, what am I saying? No, never mind, go ahead.
Yeah, so remember one of the equivalent definitions of continuity is that a function is continuous if for any convergent sequence, or in this case, think of this if you like as a sequence of points converging to x, limit of f of t converges to f of x. Yeah. Yes?
Is there a reason you defined t to be in the open interval while f is defined on the closed interval?
Yeah, the only reason here is that if t were an end, if x were an endpoint, you don't want to include the endpoint.
But we already find t not equal to x anyway.
Yeah, but if you're inside the interval, then you might as well restrict yourself to an open interval. Okay, so let's see. Question. What about the following question? If f is differentiable, well, then clearly f prime exists, but must f prime be continuous? On AB, must f prime be continuous? How many people say yes? How many people say no? Okay, give me an example. Or is it just a feeling you had? Just a feeling? Okay. Yeah, it's a good feeling. The answer is no. And let me give you an example. Consider the following function. Well, what's the source of many good examples in analysis. How about the topologist sine curve? But let's multiply it by a function that makes it have a different amplitude besides 1. The amplitude will be x to the 4/3. And let's define it to be 0 if x is 0. And if this is f if x is non-zero. So let's just see what that function looks like. Oh, what fun. This is cool. Let's see. Looks something like this. If you remember, the topologist sine curve oscillates more and more as you get closer to x equals 0, yes? But now I'm multiplying it by x to the 4/3, so this thing's going to have an amplitude which is governed by the curve y equals x to the 4/3, okay? Which you can verify. You know, this is exponents between 1 and 2, right? So this thing lives somewhere between the straight line and the parabola, right? Okay, and it does something like this. Right? Similarly, on this side, it starts off with low frequency, and then it gets to a higher frequency. And then right at the origin, it's a single value. It's 0. Okay? Okay, cool. So first of all, would you agree this function's differentiable? Tell me why. Well, away from 0, it's clearly differentiable, right? Just because it's defined by this function sine 1 over x, okay? But what's happening? Where's the only place you might worry if it's differentiable? 0. So tell me why, if you start looking at secant lines with one end at 0 and the other end somewhere else, why this thing actually is going to have a limiting slope, the secant line. Very good. Yeah. So this envelope function is going to squeeze the secant lines wherever you start putting them enough so that if you blow this thing up, you blow this picture up, it'll look more and more linear, like a line, as you blow that up. Yes. It would not be differentiable either. Yes. Yeah. No matter what you defined it to be doing at 0. Yes, and you're going to explore this in your homework a little bit. Yeah, this thing could actually. Let me come back to your question in a sec. But we just need this. Let me come back to your question in just a sec. Okay. Let's see what happens to the derivative. So you agree this thing's differentiable, but what's its derivative going to be? This is actually getting at Bonnie's question already. So if this is f, suppose I decide to look at f prime. Well, first of all, what did we decide its slope was at 0? 0. Now, for the other part, it's very easy to apply our differentiation formulas from calculus to see what the derivative of this is. Right? What's the derivative of this part? Well, let's see. It's this times the derivative of this plus this times the derivative of this, right? But what's the derivative of this become? Good. You get x to the 1/3, right? Times sine 1 over x. And then the other part basically is going to also do something funny with, take the derivative of this, 1 over x squared. It'll turn this 4/3 into minus 2/3, etc. Okay, so basically what you find is one of the terms blows up, and you get a picture that looks something like this for the derivative. Up and down forever. Don't make me do it. All right, and up and down forever on both sides. And so what you find is, hey, this thing has a derivative everywhere, but the derivative function is not continuous. Okay? Now, Bonnie, do you see why I might have chosen 4/3 here? Yeah, so if this thing happened to be less than 1, I'd be in trouble just in making this differentiable. So it has to be bigger than 1 to make this differentiable. And it has to be less than 2 to get this to blow up. Yes, good. Excellent. No. It just needs to be a number between 1 and 2. Okay. Okay, so the answer is no. There are some things you can say. If you read the book, you'll see that, in fact, that even though the answer is no, it's not always continuous, f prime does always satisfy an intermediate value property. And not only that, but you can also say f has, it never has simple discontinuities. F prime has no simple discontinuities. They're always of the second kind if there are discontinuities. Okay, great. So this actually points out something that I guess it'd be worth mentioning, and that is we have a name for functions whose derivatives are continuous. Okay, because the derivatives aren't necessarily continuous, are they? So we call, this is not in your book, but it's terminology that's become very standard. We call a function f, we say that it is C1, a C1 function, if f prime exists and is continuous. And f prime is continuous. Okay? So this is an example of a function that's not a C1 function. Okay? This C is usually scripted, and it's supposed to remind you of the word continuous. Okay? So it has a continuous first derivative. All right? Similarly, we'll call a function ck if what? If it has how many derivatives? K derivatives, and the kth derivative is continuous. If kth derivative, which is sometimes written f with a parenthesis k, exists and is continuous. Okay. Now, you might ask yourself, well, how do I even know there are other functions that are, are there functions that are C1 but not C2? Or functions that are C2 but not C3, for instance? What do you think? Well, probably because I've got names for these things, right? How do you think I might construct such functions? Vary the exponent here. Okay, between 1 and 2, you'll get functions that are C0, those are continuous, C0 but not C1. Okay, and if this is between 2 and 3, you'll get functions that are C1 but not C2, etc. Okay, so you can construct whole classes of these things. All right, so I should mention C0 is a special name. This is continuous functions. And if you take derivatives many, many, many times, and if all the derivatives exist, we have a special name. Those are called C infinity functions. All derivatives exist. And we also have another name for C infinity functions. they're called, not surprisingly, smooth. So if you hear the term smooth in mathematics, it's actually a technical term. It means all the derivatives exist. Okay? And are continuous. Well, if they all exist, then the previous one is going to be, yeah, so they're clearly continuous. Yes? C0 just means continuous. No, this function is C0 because it's differentiable. I mean, because it is continuous. Well, it's continuous, so it makes it C0. It's not C1. It is C0, but it's a little more than just C0, but it certainly is still C0. The way we've made this definition, C3 functions are also C2 and C1 and C0. That's true, but but C0 refers to continuous function. Yeah. Okay. Excellent question. Great. So, very good. What else can I say? So I said this mainly for culture because you'll hear this term, and many of you already have heard this term in other courses. What else can we say? Well, here's something that follows from the fact that f is a limit. So if f prime is a limit, well then I claim it follows from properties of limits of functions a lot of the rules that you're familiar with, right? Then you have the sum rule for limits of derivatives and product rule and the quotient rule. They all follow. And I'm not going to do these all. I'm just going to give you an example, just sort of see why this is true. What we're saying is you give me two functions. The derivative of a sum is a sum of the derivatives. I claim this follows from the fact that what? The limit of a sum is the sum of the limits. Thank you, Maya. So because the sum of a limit is the limit of a sum. Sums. Okay? Sum of limits, limit of the sums. Okay, let's see. Product. Well, what does this say? This say if you take the product of two things and you take their derivative, that's what? F, everybody should know this, f prime plus fg prime. Okay, where does this rule come from? Well, here's one way to think about it. Suppose I let h be f times g. H of x is f of x times g of x. Let me give you a picture proof, or picture motivation here. The book doesn't do this, but it's always helpful to have some picture in mind. Imagine this is the size, h is the size of a box, whose height and width are given by f and g. And as you increase the argument, which you might think of as time, this box is growing. Okay? So imagine at some time f of x, you have this particular width and this particular height, f of x, g of x. But then at some time a little later on, the height is f of t, and the width is g of t. Yes? So the rate of change of h would be looking at the area of the box, the change in the area of the box with respect to the change in time. Yes? But what is the change in the area of the box? Would you agree it's just this region here? But the change in the area of the box can be written in terms of two rectangles. Yes? So notice if then, what do you notice? You notice that h of t minus h of x is, in one case, the area of the box is, the width is f of t, that's this height here, f of t, times g of t minus g of x plus g of x, which is this length here, times what? F of t minus f of x. And you see what you might then do? I'll take both sides and divide by t minus x, which is the quotient I'm interested in, yes? And now look at this. This divided by t minus x gives me the quotient associated to g. This divided by t minus x gives me the quotient associated to f. And now I'll do what to if I'm interested in the limit of this, I'll take the limit of this, limit of the products, product of the limits. What happens to the limit of f of x as t goes to x? It goes to f of x because f is continuous because it's differentiable. Okay? That gives this. That's that f, right? And then this goes to g prime. Whereas this is already g of x, that's there, and this goes to f prime. Okay? But it comes from, the intuition comes from this picture. If you just read the proof, of course, you'll see this and you'll say, what in the world? Where did they get that? It just comes from the intuition. Okay, I'll let you figure out how to motivate the quotient rule proof that's in the book, but you might take a look. Okay. Just because this is analysis, let me show you some interesting functions that you'll enjoy. So here's a question for you. We've seen functions that are continuous but not differentiable. In this case, it's not differentiable at some point. If you have a function that's continuous, must it be differentiable at some? I mean, it may not be differentiable everywhere, but must it be differentiable somewhere? Suppose you have a continuous function, like that's a continuous function, right? Here's another continuous function. Of course, is this differentiable everywhere? No, not here and not here and not here, maybe, right? But it seems to be differentiable at other places. So here's a question for you. If you have a function that's continuous, must it be differentiable somewhere, even if it's not differentiable everywhere? How many people say yes? How many people say, oh, okay. How many people say no? Okay, everybody form an opinion. I just want to see where your intuition will take you. Continuous function, must it be differentiable let's say continuous function on the whole line. Must it be differentiable somewhere? How many people say yes? How many people say no? Okay, more of you said yes than no. But in fact, the answer is no. So here's a theorem. There exists functions, some of the strangest functions you'll ever meet, that are, let's say from R to R, that are continuous everywhere, but differentiable nowhere. What? Really? In other words, we have a continuous function that is just so jagged that nowhere. Okay, I'm just making something that looks plausible. It's so jagged that nowhere has a derivative. Really? Show me a function besides something that looks like this. Okay, well, here's one. When I write this down, of course, you'll be able to see at least why it might have this feature, but there's some funny things about this function. So consider the following function. Let's take the sum of a bunch of functions, each of which are cosines. So there's the first part here. Okay, cosine of something. I'll just put the pi in here just for fun. Okay. And what I'm going to do is I'm going to let this sum go from n equals, doesn't matter here what it starts at, 1. Okay. And it's going to go, well, I'm going to let it go to something here. Okay, you have to guess what. I'll give this thing an amplitude, but I will raise it to the nth power. Not an amplitude, sorry, this affects the frequency, right? Then I'll give this thing an amplitude, and I'll raise it to the nth power. And now what? What am I adding up? Well, these are a bunch of cosine functions, right? So they're wavy like this, yes? But as n grows, they get what? Higher frequency. And, well, taller or shorter depending on, well, I haven't told you what A and B are, so I have to tell you, actually, don't I? So I'm going to let B be between 0 and 1. We'll fix B between 0 and 1. And I'll let A be an odd integer. Okay. And I'll choose A and B so that together their product is bigger than 1 plus 3 pi over 2. Okay. This product has to be big enough so that this thing, as it gets more jagged and thinner, it doesn't suddenly, if this weren't true, the thing may not look like this in the limit. Okay. Okay, good. So it's about sum of a bunch of cosines, and then what? How many of them should I add? If I add only finally many of them, this is just the sum of continuous functions, which is continuous, right? So here's the thing that the big kicker that makes this thing way more interesting. It's a sum of a bunch of, it's an infinite sum. Okay? So point-wise, this is a series. Okay? But as a collection of functions, it's an infinite sum of a bunch of functions. And of course, you can't say, as we'll see, that the infinite sum of a bunch of continuous functions is necessarily continuous. We have no theorems like that yet. Okay? Yet. Okay? Analysis 2. Okay? We start talking about sums of continuous functions. Actually, I'm going to say more about this next week, just to give you a hint of what's coming in analysis 2. But let me show you what the picture then looks like. So, the first function looks something like this, right? And then on top of that, you add a second function, which has a higher frequency and also smaller amplitude. So you're basically adding a wavy function on top of a wavy function. So it looks like this, yes? And then the third stage, you're adding something that's a little more, has a higher frequency and smaller amplitude. So you're basically adding up a wavy function that's has a little more amplitude, yeah?
What you're drawing is what it looks like after you sum the third two terms.
I'm showing you the partial sums of this sum of continuous functions, okay? Good. And then the fourth one, I'm not going to draw, but you can imagine is basically going to add a little more jaggedness. And the claim is in the limit, because this is a limit of a bunch of partial sums, you'll get something which happens to be verifiably continuous. I'll show you how to verify that next week, okay? But also verifiably not differentiable, okay? Kind of a very cute function.
Can that function essentially be described as a fractal function in some way?
Yeah, I mean, this is.
That's how you can get a lot of properties out of that, I feel like.
Yeah, I mean, if we haven't defined what a fractal is, but this, if anything's a fractal, this certainly is. Yes, definitely. Okay, very cool. So what I want to do after the break is I want to show you a theorem, which is probably the most important theorem about derivatives, and that's the mean value theorem. Okay, so let's take a couple-minute break. Let's resume. Oh, yeah. So I think A range is basically 90 and above. B range is like 78 and above. C range is like 65 and above. Okay. Come see me if you didn't do as well as you would have liked. Okay. We talked about this. We talked about some of the problems last time. Okay. Good. So what did we do before the break? We talked about differentiation. We talked about what the derivative is. And what I want to do now is tell you about a theorem that basically is the big workhorse in terms of proving anything, and proving lots of things about derivatives. And that's something called the mean value theorem. So the mean value theorem is something that some of you have encountered in your calculus courses. And I'm not sure that in those courses you got a sense of why we love and care so much about the mean value theorem. So let me first say what it is. So it says if f is continuous on, let's say, some closed interval and differentiable on the open interval, AB, then the claim is there exists some point, C, inside AB, such that the following is true. Such that f of B minus f of A actually is equal to B minus A times f prime at this mysterious point C that we claim exists. Okay? This is the mean value theorem. Let me point out to you that this particular equation, which if you don't mind I'll call Smiley. One way to think about what Smiley is saying is the following. If you have a function and it is, let's say, looks something like this, what we're saying is if you have a point A and a point B and the function is defined on AB and it's differentiable everywhere inside, well, look what happens if I divide f of B minus f of A over B minus A, if I move this over. Don't you agree that what I get then is the slope of the secant line? And what we're saying is this slope of the secant line, f of B minus f of A over B minus A, is actually equal to the what? Yeah, do you see a point in between that has the same slope? Instantaneous slope? Might be right here, for instance. Okay. So what it's saying is there's a point in between that has the same slope as the secant line does between these endpoints. That's another way to think about what this theorem is saying. So what's the big deal? Yes, question. Well, I mean, it's certainly true if you close this interval, but this is the weakest conditions that you need. You don't need it the limits to actually the limit of the quotient of the derivative limit to exist at the endpoints. We're just, I mean, it could be one of these crazy functions where it doesn't have an endpoint limit. The derivative doesn't exist at the endpoint, but it exists everywhere inside. Okay. Think some weird sine 1 over x function that does something weird as you get close to the endpoint. Okay, so let's see. What's the big deal with this theorem? Well, here's the big deal. Okay. This is really the only theorem we have that connects the value of the function to the value of the derivative, okay, without involving limits. Okay, so notice that what Smiley does, it connects the value of f to the value of f prime somewhere, right? Without using limits. I mean, obviously the definition connects the values, but that's what's nice about this. So anytime you have a statement which kind of feels like, okay, you know, there's a lot of places in calculus where you prove things in a hand-wavy way. Well, if you want to make hand-wavy precise, you go back to the mean value theorem. So let me give you some examples here. Here's a sample application. Well, suppose you have a function whose derivative is bigger than 0 for all x in AB. What can you conclude in a hand-wavy sort of way if the slope is bigger than 0 between a and b? Then show, let's suppose this is our problem, show that f of b, what's the relationship between f of b and f of a? One has to be bigger, right? The one that's going that way, yes? Oh, well, here's a very easy proof. Actually, you can even say more, right? You can say this thing's strictly increasing, right? Why? Well, here I have some statement about the derivative, and here I have some statement about the values of the function. Well, let's see. And I don't want to go back to using limits. Oh, look, here, statement about function values and derivative. Oh, interesting. Okay, so what can I say about f of b minus f of a? And what am I hoping to show is true about f of b minus f of a? Hoping to show is positive. Well, by the mean value theorem, this is b minus a. Oh, yeah, show b if, yeah, b is to the left of a. Good. Times f prime at some point in between. Do I know what point? No. Does it matter, though? No. Why? What do I know about this creature? It has to be what? Positive, because it's one of these points. That's positive. What about this? That's positive. So this is bigger than 0 as desired. This gives us the fact that f of b is bigger than f of a. Done. Okay. Very nice applications. Very easy to see as true from the mean value theorem. Okay. We'll see many more such applications, and you will definitely see some on your homework. I mean, basically, all the problems in Chapter 5 are some version of the mean value theorem, okay? But let's see why this is true. Proof. Why is the mean value theorem true? Why is this picture, does this picture suggest why this theorem is true? What am I claiming? I'm claiming that there is a point where the slopes, the limit of the secant lines on one side and the other, because the derivative exists, actually agrees with the limit of the slope of the secant line. Just to give you a non-example, think about the following picture. Suppose I had this function. Is it true that there is a point in between a and b that has the same slope as this secant line? No, what failed? Differentiability. Now, okay, so why did it fail? Well, look, on one side, the secant line slopes are less than this slope. On the other side, they're bigger than this slope, yes? Now, of course, what happened here is if you took these secants from this point, on this side they're smaller than this slope, and on this side they're bigger than this slope, but what kind of happened in the middle? Well, they got equal, right? Okay, so how can we sort of get wrap our heads around this idea? So here's a way to go. So the first thing is, let's just look at a special case. Would you agree? Let's say the following. Let's turn this picture on its side. Would you agree if you have a function, let's say h, that happens to be differentiable, would you agree that at its local maximum, that's where the slope is 0? H prime here is 0. Would you agree that it happens at the local maximum? Well, why did that not happen here? At the local maximum, h prime does not exist, right? So somehow the existence of the derivative is going to help me, yes? And what can you say about a local maximum? So let's write this down and as you think about it. If h on AB has a local max at AB at some point C inside AB, closed AB, and h prime exists, h prime of C exists, then I claim h prime of C must be 0. That's my claim, yes? Okay, well, this is actually not bad, not hard to show. Here's the idea of the proof. Just take a look at what you're taking the limit of. Look, suppose I look at h of t minus h of c and compare that to t minus c. If h has a local maximum at the point C, what has to be true about, let's say, h of t minus h of c, no matter which side I'm on, if it has a local maximum at C? This thing's going to be what? Negative. It has to be negative because C is a local maximum. Yes? Okay. But now, what about the bottom? Well, on the bottom, it depends on which side you're on, yes? So would you agree, if you examine this creature, this thing could be positive or negative, but the top is always negative. So what you see is that this thing is going to be, the whole thing is going to be negative on the right, if t is bigger than C. And it's going to be positive on the left if t is less than C, yes? So we're taking the limit of this, a bunch of positive numbers on the left, a bunch of negative numbers on the right, and if that limit exists, what has to be true? Well, the left and the right-hand limits have to exist and be equal. So if you take the limit of a bunch of positive numbers, what's the only values that can be? 0 or bigger. And if you take the limit of a bunch of negative numbers, that can only be 0 or smaller. So what's the only thing this derivative could be if it exists? 0. That's the argument. So it's negative on the right. So since the left limit and the right limit exist and are equal, the limit must be 0. Okay? Everybody happy with that? That's a simple version of I think this is called Rolle's theorem. Okay, something like that. Okay, great. Now, suppose that is true. How will this enable me to prove the mean value theorem? Well, how is this picture kind of like this picture? Yeah, it's just a little off. So really, if I wanted to do this to apply this mini result to a general picture, I should just take the function and subtract off the function that is the what? Secant line. And then you get a new function, let's call it h, that has the requisite properties. Okay, that's the idea. Now, I just said that in words, and you can carry that out. What I do want to do instead is actually prove something a little more general, since we have the machinery, and this is called the generalized mean value theorem, which says the following. If f of x and g of x are continuous on the closed interval and differentiable on the open interval, then there exists a point in between, let's call it C, so that what? F of b minus f of a times g prime of c equals g of b minus g of a times f prime at c. And I want you to notice again that this point C, I don't know anything about except it's in the interval somewhere, appears on both sides of this equation. Why is this called the generalized mean value theorem? Yeah, g of x could be x. And if you do that, you get the regular mean value theorem. So notice, if g of x equals x, we get the mean value theorem. Because the derivative is 1, and this becomes b minus a. So let me prove the generalized mean value theorem, and we'll use our first observation. Number 1, mini observation 1. Okay. So here's the idea. Again, the book doesn't do this, but it will motivate the proof nicely. So the idea is the following. Suppose I have suppose I have a cake here. Okay, this is a piece of cake. And let's suppose that I have a knife that's going to sweep over the cake, like so, left to right. Okay? And the position of the knife is given by the left to right knife. The position of this knife is given by a function f. So this tells me where the knife is. Okay? And it's going, maybe it doesn't even go left to right, but the point is the position of the knife is given by this. But you can imagine sweeping it from one side to the other. Okay? So that at time A, the position of the knife is at f at A, and at time B, the position of the knife is at f of B. Okay? And it's moving around, yes? Suppose simultaneously I have another knife whose position is given by g of t. Also, at time A, it's at the bottom, and at time B, it's at the top. Okay. Okay, so this is the knife. I'll call this knife big A. I'll call this knife K and call this knife L. Okay. Okay. Well, let's see. I claim in this particular expression, let's call this expression Cyclops Smiley. I claim that the left-hand side of Cyclops Smiley represents what? Well, I claim that this is the rate. If I look at f of b minus f of a, that is this distance, yes? Times, well, g prime of c is the rate at which this knife is sweeping out length. So this product is the rate at which the area gets swept out. It's the rate that knife L sweeps out area, of cake. Similarly, the right-hand side of Smiley, Cyclops Smiley, is the rate that, well, let's see, it's g of b minus g of a, so that's this width times the rate of change that the knife is moving, yes? So that's the rate at which k sweeps out area. Yes? Okay, so what do you think this theorem is saying in terms of knives and areas? What's it saying? Imagine knife K starts at one end and moves to the other end, and knife L simultaneously starts at one end and moves it to the other end. And when they both start, they've swept out no area. They both ended, they swept out the complete cake. So what this theorem is saying is, if they both sweep out the total area in the same interval a to b, then at some point their rates must be the same, right? Because if one knife was sweeping out more area than the other at a greater rate, it couldn't be the case that they'd both start and end and sweep out the same area. It's basically what it's saying, right? Okay, so if you see that, then you see exactly what function to apply h to. So basically, here's the function you consider. Consider h of x, which will be f of b minus f of a times g of x minus g of b minus g of a times f of x. And this is, if you like, the difference in the areas swept by time x. That's the function to look at, isn't it? Why? Well, because then it's clear that h of a has to be what? At time a, when they both knives start, they both swept out how much area? Nothing, right? 0. It's also clear that by the time they both finish, the difference in area swept out is what? It's also 0. So if you have a function h that starts at 0 and ends at 0, then what can you conclude about this function? I mean, who knows what this function looks like? But would you agree that it must have either a maximum or a minimum, right? I mean, that theorem's true whether it's a max or a min, right? But there's some point where this derivative in between is 0, right? So by 1 implies there exists a c such that h prime of c is 0. Okay, but guess what's true about h prime? What is h prime if you calculate it? But h prime of x equals, take a wild guess. It's the difference between the right-hand side. Is it the right and the left, or left and the right? It's the left-hand side minus the right-hand side of Cyclops Smiley. That's the argument. If you take a look at the book's proof, basically the book starts with this and then says, oh, take a look, ha, 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 look, these are satisfy the thing you need, but you have no intuition where it comes from, right? So this is the picture that helps make that precise. Okay? Okay, so this is basically the workhorse to do most of the problems in Chapter 5. Next time what we're going to do is I want to tell you about one other theorem about derivatives, and that's Taylor's theorem. And it wouldn't surprise you that Taylor's theorem is proved using the mean value theorem. Okay?